Anti-differentiation by substitution, 6-2. Let's just jump right in. I do have a little 5-point quiz for you, quick review quiz. You are, for number 1, evaluating the definite integral. I want you to do that by hand. And then 2, 3, 4, and 5, I want you to find the derivative of those 4 items. Alright, what we are learning about indefinite integrals, we've talked a little bit about them already, and the fact that their answers are a family of functions. Substitution in indefinite, substitution in definite integrals, those two things go hand in hand. And then we're going to introduce separable differential equations, which is actually a big part of 6-4, but it'll be nice to kind of introduce it a little bit, and then we'll be a little bit ahead of the game in 6-4. Anti-differentiation techniques were historically crucial for applying the results of calculus. Okay, I went through and I put in here some of the basic rules for antiderivatives, which the first one is the power rule, and hopefully when you look at that, it looks a little nasty, but it really isn't. If I have a function u to the n du, and I'm taking the antiderivative of it, remember I just add 1 to my power, and then I divide that function by that power, and I put a plus c on the end. The only time that works is when n is not equal to -1, because if n is equal to -1, what you should remember is that if 1 over u, which is u to the negative first, is my derivative, the function that had that as a derivative was the natural log function. Now, because of how natural logs work and how derivatives and antiderivatives work, when you are going backwards and you are given the integral of 1 over u to u, the answer is the natural log of the absolute value of u plus c. We need to make sure that we discuss that in class, so maybe somebody put a little note there to remind me to do that tomorrow. Trigonometric formulas. These are all just your derivatives backwards. So the integral of cosine is sine plus c. The integral of secant squared would be tangent plus c. The integral of secant tangent would be secant plus c. The integral of sine would be negative cosine. The integral of cosecant squared would be negative cotangent. And the integral of cosecant cotangent would be negative cosecant. Okay, and these are all just the derivatives that we learned earlier. We are now just going backwards and saying what their antiderivative is. Exponential and logarithmics. Nice. E is really nice because we knew that the derivative of e was e, so the antiderivative of e is e. We had the antiderivative here of a to the u, and that is just a to the u over the natural log of a. The antiderivative of the natural log of u is u natural log of u minus u plus c. If I actually did the product rule here, found the derivative of this using the product rule, minus the derivative of this would just be 1, I would end up getting natural log as my derivative. Okay, so just know the derivative or the antiderivative of the natural log of u is u natural log of u minus u plus c. And then the antiderivative of the log function, if I gave you log a of u, we could rewrite that as the natural log of u over the natural log of a, right? This is our change of base formula that allows us to type it into our calculator. What you should recognize is that the natural log of a is just a constant, which I am allowed to pop that out, and then I have 1 over the natural log of a times the antiderivative of the natural log of u du, which just brings it back to this. So here is our antiderivative for anything other than natural log, which isn't really too difficult to remember. You just want to know that the natural log of a is just going to be a constant that can float along with my natural log of u function's antiderivative. Alright, so let's get into the meat of this lesson. The chain rule allows us to differentiate a wide variety of functions. However, we are able to find antiderivatives for only a certain range of functions. sometimes we are able to use substitution to rewrite functions in a form that we can integrate. So while we learned a lot of different rules to find derivatives, there are a limited number of rules to find antiderivatives, but here's one of them that we're going to talk about today. Let's just say I gave you the antiderivative of x plus 2 square, the quantity x plus 2 to the fifth dx. What we're going to do is we're going to take the inside function x plus 2 and we're going to just rewrite that as u. Now the derivative of u would be the derivative of this, which would just be 1. But if I multiplied my dx to the other side, I'd have du is equal to 1 dx. What I'm going to do is then rewrite my integral as u to the fifth du, because I've said that dx is equal to du. Now I have a function that I have the power rule for that I can integrate. So I know that I just add 1 to my power and I divide the function by that power. So I have 1/6 u to the 6th plus c. I have to remember, however, to substitute that x plus 2 back in, and so my final answer is then x plus 2 to the 6th, all divided by 6, plus c. So this is the general format of how we're going to use substitution to find the antiderivative. So let's do this one together. I have the integral of the square root of 1 plus x squared times 2x dx. One of the basic clues we want to look for is if we can find the function and his derivative together. And so if I notice here, 1 plus x squared would have a derivative of 2x, which is nice and conveniently put right there for me. So another thing you want to look for is the composite. Usually the inside function is the u that we're going to take out. The derivative of 1 plus x squared is 2x dx. So I'm going to say, okay, u is then 1 plus x squared. Du then would be 2x dx. All I did to find that is I now focused my attention over here. So 1 plus x squared, the derivative of that would be 2x. I just took my dx to the other side. So I just rewrite stuff. Now I have the integral of u to the 1/2. This is all under the square root, so I said that 1 plus x squared is u to the 1/2 du. I add 1 to my power, so that'd be u to the 3/2, and I divide it then by that 3/2, which is the same as multiplying by 2/3. And then I just remember at the end to put my 1 plus x squared back in, and there's my antiderivative. That's your process every time. Seems kind of complicated at first, but it'll start to get better with practice. Note this only worked because 2x was in the original. Many integrals cannot be done by substitution because oftentimes if I had just, the square root of 1 plus x squared dx, this 2x was not there, and that tells me that I am not allowed to use substitution to find that integral. All right, so we have the situation here where my inside is 4x minus 1. So I'm going to say, okay, he's going to be u. Therefore, du would be 4 dx. The problem, however, is that I do not have a 4 inside. But what I could do is I could put a 4 inside and balance it by putting a 1/4 on the outside. Constants allow me to be able to do that. So now I have the integral of u to the 1/2 times 1/4 du. That 1/4 can pop to the front. So now I add 1 to my power, divide off by that power, and I now, when I clean it up, have 1/6 u to the 3/2 plus c. Don't forget, put that u back in. 4x minus 1 goes back in for u. So I have 1/6 quantity 4x minus 1 to the 3/2 plus c. All right, let's look at some trigonometric ones. If I have the integral of the cosine of 7x plus 5 dx, my inside function is going to be 7x plus 5. So if I find the derivative of that, my derivative of u would be 7 dx. So I'm now going to say, okay, if I need a 7 on the inside, I need to balance it on the outside with a 1/7. So I now have the cosine of u times 1/7 du, which gives me the integral of cosine is sine, so I have 1/7 sine of u plus c. 1/7 sine of 7x plus 5 plus c. Next example, sorry, there's a lot of examples in this section. So if I have the integral of x squared sine of x to the third dx, I'm looking here to see if I have something that could be the derivative of something else inside. I notice I have an x to the third there. The derivative of an x to the third is going to be an x squared. So let's make our x to the third u. Du would then be 3x squared dx. Well, I have a 3, or I need a 3, which I don't have. So I put a 3 here, balance it by putting a 1/3 on the other side. So now I have 1/3 sine of u du. The integral of sine is negative cosine. So I have negative 1/3 cosine of u plus c, and we just replace our u then with x to the third. Pretty handy, right? So you are looking for derivatives along with his original function inside of those integrals. Now I have the integral of sine to the fourth of x times cosine of x dx. If I rewrote sine to the fourth, I would write it as the quantity sine of x all to the fourth power. So hopefully you've recognized that u is going to be the inside function sine of x. You want to, in general, make your u that inside function. Du would then be cosine of x dx, which, that's nice. I already have that there. So I'm just going to replace cosine of x dx with du. So when I rewrite this, I'll have the integral of u to the fourth du. Integrate 1/5 u to the fifth plus c, and then replace 1/5 sine to the fifth of x plus c. Next example. What if I gave you a definite integral of the integral from 0 to pi over 4 of tangent of x secant squared of x dx? It works exactly the same way, actually. If I'm looking here, I'm going to say, okay, u is going to be tangent of x because I see that tangent's derivative, secant squared, is already there. So du would be secant squared of x dx. The problem, however, is that these limits, 0 and pi over 4, are meant for x, not u. So we can do this a couple different ways. Here's the one way you can do it. You can find new limits by just putting 0 and pi over 4 into your u function. So the tangent of 0 is 0, and the tangent of pi over 4 is 1. These are now my new limits, 0 and 1. So I rewrite everything now in terms of u. I integrate it, 1/2 u squared. Remember, with definite integrals, I don't need the plus c. And I'm just going to integrate that from 0 to 1 now instead of 0 to pi over 4. So when I put 1 in, I'll get 1/2. When I put 0 in, I'll get 0. And my final answer then is 1/2. So the area under the curve of the tangent of x secant squared of x function from 0 to pi over 4 is just 1/2. Here's the other way you could do it. Using the original limits, I still have the same u, I still have the same du, I still throw in u and du, but I don't want to use 0 and pi over 4 as my limits yet. So let's just write it as an indefinite integral, integrate it, put it back in, my tangent of x function goes back into my original for u, and now I can put 0 and pi over 4 in. So it really is whatever method you like to use. I do usually use the second method, but you do have to be careful not to forget to substitute back in first. Okay? Alright, and the next little introduction part we're going to do is separable differential equations. So, a separable differential equation can be expressed as the product of a function of x and a function of y. This basically takes care of some implicit differentiation where we would have x's and y's in our function, and we're trying to find the antiderivative of that. So, example, if I gave you something like dy dx, the differential equation dy dx is equal to 2xy squared. The problem is that we have this in terms of both x and y. So if I was asking you to solve it, which basically means find the antiderivative, we would have a little bit of trouble. So here's how we're going to go through and do this. You want to get all of your y's and dy's and all of your x's and dx's on each side. So what I'm going to do is get rid of this dx by multiplying it to the other side, and then dividing off this y squared by getting rid of, so that he goes over there. So I now have dy over y squared is equal to 2x dx. If I send that y squared to the top now, I have y to the negative 2 dy is equal to 2x dx. Now to solve it, you're just going to integrate both sides. So it's really not too difficult. I integrate this y to the negative second. I just use a plain old power rule. So I have adding 1 to my power, dividing by that power here, plus his constant, and then that's equal to his antiderivative, which is just x squared, plus his constant. What I can then do is just combine the constants together so that I now just have negative 1 over y is equal to x squared plus c, and I've just solved that differential equation. So your whole process, and I guarantee there will be something on the AP tests to separate your equations and find the antiderivative, but you need to just get all your x's and dx's on one side, all your y's and dy's on the other, and then integrate both sides. If I then solved it for y, my y multiplies the other side, then I can divide off that x squared plus c, and so that's how they came up with the negative 1 over x squared plus c is equal to y. So let's look at this one. You see here that we do have a 1 plus y squared multiplied onto a 2x and e to the x squared. So we recognize this right now as a function that I need to separate out my variables, get everything that's the same on each side. So I'm going to send my dx to the other side by multiplying it over, and my 1 plus y squared is going to get divided off. So here are my y's, here are my x's, and then I just find the antiderivative. So I now have on this side over here 1 over 1 plus y squared, and on this side 2x e to the x squared. So what I'm going to do here is on this side recognize that, oh, this x squared is inside. I see that 2x is his derivative, which is on the outside, which is there. So let's set u equal to x squared. Therefore du would be 2x dx, and I can rewrite him as the integral of e to the u du, which is the antiderivative of just being e to the u. And then what we also need to recognize over here is that 1 over 1 plus y squared is actually the derivative of the arctangent function. So inverse tangent of y plus c1 equals e to the u plus c2. Don't forget to substitute back in your x squared for u. Combine your constants, and you have inverse tangent of y is equal to e to the x squared plus c. When I solve that for y, because right now it's an implicit function of x, when I solve it for y, it's now an explicit function of x. I'm just going to solve it by taking tangent of both sides. Now my tangent and inverse tangent cancel. I'm left with y on that side. Final answer, y is equal to the tangent of the quantity e to the x squared plus c. That c has to stay inside because you are not allowed, hopefully you can remember this, you are not allowed to just distribute a tangent. It is a function. It is an operation. It's not something that's just a number that you can distribute it in. You cannot distribute in operations like tangent or natural log. I know you may not love this section as much as I do, because I love it a lot, but you probably don't love it nearly as much as I do. But here are my words of wisdom. Have a great evening, and we will see you tomorrow. Don't forget your 5-point quiz. Bye, everybody.